All right, everybody, welcome back. We are now going to look at our last video in the geometric series section, which is all about those infinite geometric series. I have a cool little picture here. We'll explain what that means at the end of the video. Let's just think about the example we were doing at the very end of the last video, though, which was a sigma notation where the common ratio was 3. And I think in the last video we were going up to the 12th term or something like that. But what if we're just going to a mystery term, maybe an infinite term? Well, one way to explore what's happening with these sums, instead of writing them out the long way, is to consider what is called the sequence of partial sums. The sequence of partial sums is effectively the sum of the first two terms. The first term is 1/2, and then we could do 1/2 plus 3/2 is 4. Is that 4? No, it's 2. Thanks. And then I could do that plus 9/2 and get an answer. And I could do that plus 27/2 and get an answer. And then instead of just looking at the total, I could actually look at the sequence of how the sums are growing as the number of terms increases. Now, this is fun to do by hand, and it's fun on your calculator, but it's the most fun to do in a spreadsheet. And that's what I have over here. So, we have a first term of 1/2 and a common ratio of 3. We're just in Google Sheets here. You can do this in any spreadsheet program you want. I've programmed the partial sum of the first n terms using the formula. You can stare at that formula for a second if you want, but I've used the n, the first term, and the common ratio and plugged into the formula we proved in the last video. So this is the finite series formula. I'm not being infinite yet. I'm being very finite, annoyingly finite even. And the first term is 1/2, and then the second term, like we said, 1/2 plus 3/2 is 2. You add the third term, you get 6.5, and here's the magic of spreadsheets. I can just drag this down to the edge of the screen, and we'll think about it for a second and repeat the pattern. Now, we can see, so this would be the sum of the first 21 terms, for example. Let's add some more. Let's see if we can break the spreadsheet. All right, so oh no. I see, because I didn't copy enough to copy the pattern. There we go. If we copy enough to copy the pattern, at some point we get down here, and we haven't broken the spreadsheet, but we have exceeded its display powers. We're into scientific notation. There'd be 21 zeros on that number. So that's pretty big, and that implies that this sequence, if I take an infinite sum, right, if I say, all right, let's go to infinity and have as many terms as I want, then this is also going to trend towards infinity. As n trends to infinity, the sum would also trend to infinity. That kind of makes sense. We're adding bigger and bigger numbers every time. But what about a series where I'm adding a smaller and smaller number every time? Let's flip the first term in the ratio. So my first term is 3, and my ratio is 0.5. I want you to guess what's going to happen because you're going to see the answer as soon as I type that in. Think about what might happen to the partial sums. Do you think it's going to keep getting bigger and bigger and bigger? Or do you think it might settle down because you're only adding a smaller and smaller number every time? All right, let's put a 0.5 in and find out. So, our first term is 3. That makes sense. The second term is 1.5. But we're adding that onto the sequence of partial sums. So we have 3 plus 1.5 is 4.5. The sum of the first 3 terms is that plus 0.75, so 5.25. Then it's the next the sum of the first 4 terms is that plus 0.75 over 2. So then we get 5.625. And we're adding on every time one more term to the sum. This is the running total of the sum, but look at what's happening. Look what Excel thinks. At some point, it just says, hey, you're looking at 6 over here, right? It doesn't even take that long for you to get effectively equal to 6. And that is exactly how you can have an infinite series that corresponds to a finite value. That's going to happen anytime you have a geometric series. It does have to be geometric, and your ratio is less than 1. Your infinite sum is going to converge. This is what we call when it approaches and gets closer, we say it converges to a finite value. In this case, it appears that the series converges to the number 6. I will post this to our class and the spreadsheet and share it with you if you're one of my students. So you can play around with it on your own. It's pretty fun. You can put in any terms you want here. Put 10. See how that? Oh, so it's going to change how it converges because, of course, it changes the terms, but it's still converging. Well, let's change the ratio. What if I 0.9, right? What if I'm really close to 1? Am I going to converge? Yeah. I mean, it's going to take a little longer, but it looks like this thing is stuck under 100. What if we have a first term of, down to 3? I'm going to make a negative ratio. Negative 0.2. Ooh, right. All right, 3. So we're going down, then up, then down, then up, right? Because we're alternating down, up, down, up, down, up. But it looks like it's going to get stuck at 2.5, in fact, really quickly. Really, really quickly. So, and remember, this isn't the sequence itself that we're looking at in this column. This is the sum of all the terms of the sequence. I guess I should have had a column for the actual sequence itself, but we don't have that column. These are the sum of the terms. All right, so why is this true? How is it that we can have an infinite thing that converges to a finite value? Well, I'm going to share with you a little bit of pictures. So, let me see if I can get this going right. There's that triangle we were looking at. Let's see what this triangle actually means. This triangle represents the idea that if you have 1, so the whole unit is 1, and you shade 1/4 of it. So we're doing 1/4 plus 1/4 of the missing area. So 1/4 plus 1/16, because that little is 1/16 of the total. And then 1 over 4 to the third is 1/64th, and so on. If you nest them geometrically in this way, every piece is getting smaller and smaller and smaller. And in fact, that shaded area we were looking at is 1/3 of the total. And it is true, and this picture proves it, but we'll prove it algebraically in a minute, that the sum of 1/4 to the n, or 1 over 4 to the n, from n equals 1 to infinity, should give you 1/3. All right, so let's do some algebra. Let's take a look at our formula. This is our formula for a finite sequence. And if we imagine that we're looking at this finite sequence as it's growing and growing and growing and growing, well, we could still use this for any finite number, even 1,000 terms, we could still use this formula, but what would happen? Well, if the ratio is less than 1, and n is large, and large is however big you need it to be, then r to the n is small. Or we could say, as n goes to infinity, r to the n should trend to 0. And if r to the n trends to 0, then this thing should trend to a1 times 1 minus 0 over 1 minus r. Wait, that looks really simple. And that, in fact, is the formula. 1 minus 0 is just 1, so this is really a1 over 1 minus r. And that's the formula for an infinite geometric series. And I'll state that a little more formally in just a second. But because our ratio is less than 1 in its absolute value, we taking exponents of it, that part of the formula effectively cancels out. And we're left with just all of the nice parts, and the gross parts went away. Really, really convenient. All right, so a little more formally. The sum of an infinite geometric series. If your constant ratio is between -1 and 1, then the sum of the series, which has a constant ratio, is given by a1 over 1 minus r. That's it, and that's all. That's all you need. If, by the way, you're looking at a series sequence and the ratio is larger than 1, then we just say that it does not have a sum, or we could say that it diverges. So, we don't say the answer is infinity, we just say the sum does not exist. Now, I claimed just a second ago to you that the sum, well, I guess I should write it as 1/4 plus 1/16 plus 1/64 was equal to 1/3. Well, let's see. So that would be a ratio of 1/4, because I'm multiplying by 1/4 each time, and an A1 of 1/4. What if I use this formula? Well, it'd be 1/4 over 1 minus 1/4. That'd be 1/4 over 3/4. And those 4s are going to cross out, and you will actually get 1/3. So the algebra agrees with our picture that 1/3 of that shape is shaded when we divide out by 4 every time. Here's another picture of the 1/4 situation. Maybe you didn't like triangles. Maybe you like squares because they have to do with 4. It's pretty natural to divide those into 4. So here's 1/4. Here's our hand. There we go. Oh, no, not like that. Much better. Here's our 1/16. Here's our 1/64. Here's our 1/4 to the 4th, whatever that is, and so on. You can imagine this going infinitely on. Well, look at this diagram. We've effectively divided it into 3 sections. Here, let's color them in. You can move those over, well, like that. You could also move them up like that. And of course, you have the original ones in the middle. And so you take 1/4, 1/4, 1/4, 1/4. Turns out that fills exactly 1/3 of the total square. Isn't that cool? Isn't that nifty? And it only is possible because we're going out to infinity. That is, each piece is getting smaller and smaller and smaller and smaller. But it gets so small that we say for all practical purposes, for any tolerance that you could want, that's equal to 1/3 of the total square. All right, a couple more examples. I think the numbering is continued from the previous video, so we'll call this example 3. It's an infinite sum. I need to use the formula A1 over 1 minus R. I need to check a couple things. First, well, let's list the terms out. So if I equals 0, that's my first term. So then the first term would be 12 times 3/4 to the 0. So that'd be 12 plus, then the next term would be negative 9, because I'm doing 12 over 4 times 3, and then times 3/4 again, so that'd be plus 27/4, etc. So right, that would be the sequence we're looking at. A1 is 12, R is negative 3/4. Importantly, let's check that R is less than 1. Negative 3/4 is greater than negative 1, less than 1. So that's going to work in our formula. We're allowed to use it. So let's see what this sum should compute out to be. A1 over 1 minus R is 12. Divide that out by 1 minus negative 3/4. So that's going to be 12 over 7 minus minus. That's going to be 7/4. So that's going to be, should compute to 12 times 4 is 48. So 48 over 7. Let's go back to our spreadsheet and see if this worked. All right, so we got a first term of 12, a ratio of negative 3/4. It appears that we are approaching, we go 12, 3, 9, because we're bouncing up and down. We have a negative ratio. Eventually, we were approaching 6.857, blah, blah, blah. And look at that. That is indeed 48 over 7. So this works even if the numbers aren't nice. We can still see that you're going to approach a finite value of these partial sums. That's pretty cool. All right, let's try another. So it won't always come to you in that nice sigma notation. That's actually the easiest notation. Now here we have to look at our sequence. All right, so 3, 2, 4/3, 8 9ths. This one might look a little weird to you. You might go like, what kind of sequence is that? And I think I get thrown off by the 3 and the 2. Remember, you can just take any consecutive terms and divide them to find the ratio. So 2 over 3, right? The second term divided by the first term is 2/3. That's our ratio. Let's check though. We can do, 8 9ths divided by 4/3. We should get 2/3 again, but let's just double check. Oh yeah, that's 2, though, those reduce to 2 and those reduce to 3. So we do get 2/3. So the ratio is 2/3. And our first term is 3. So let's use the formula. The infinite sum, they just write S. You can think about it as S sub infinity. I'll just use S, is 3 over, or it's A1 over 1 minus R, which is 3 over 1 minus 2/3. That's 3 over 1/3, which is, careful with your fractions, 3 over 1 times 3 over 1, or 9. And this whole sum should converge to 9. I'm not going to check it in the spreadsheet. I'm pretty sure that it works. It is convergent. By the way, hey, this is a good chance to use your sort of logical answer checking. Say that you've done the fractions wrong, and you said, those cross out, and this is equal, those cross out, and this is equal to 1. Does it make sense that 3 plus 2 plus blah, 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 where nothing is negative, can get you to 1? No. So, even if we're dealing with infinity, you can still use your good answer checking senses and think about reasonableness in your answers. And probably that is, to be honest, the biggest source of error is nothing to do with infinity, nothing to do with geometric. It's dang darn fractions again. And there will be fractions in these because you have to have that ratio less than 1. So please watch out for that. All right, here's another one. Infinite sum. The first term, we have I equals 1 here, so I'm always checking that index. So the first term is 4 times 5 halves to the 1. Well, that's 20 over 2, so that's just 10. So that's the first term. The ratio is 5 over 2. So the sum should be 10 over 1 minus 5 halves. 1 over A1 over 1 minus R. So that should be 10 over negative 3 halves, so that's 20 over negative 3, or negative 20/3. And that should be the sum. Okay. Now, I have made a very bad mistake here, and I did it on purpose this time. There's no way that that answer can be negative 20/3. I mean, let's think about it carefully for a little bit. Is there anything that's in here that's going to make that negative at all? No, it's not an alternating series. It's going to be, the terms are all going to be positive. There's no way I could get that. Well, okay, did I use the formula wrong? No. I made a mistake with the ratio. That's greater than 1. What if we actually write out the terms of this series? We know the first one would be 10. Then the ratio is 5 halves, so that would be 50 halves, or 25, plus 250 fourths, plus, etc. The terms aren't shrinking, folks. We're multiplying by 2.5 every time. The series here has no sum. We'll say the series diverges. Because our terms don't go to 0, our ratio is greater than 1, the series diverges. You can plug all those numbers into the formula and get a result, but it's not going to be a correct result. And that's something to be very, very cautious about. Let's do another example. 8 plus 12 plus 6 plus... All right, and keep going. Okay, well, let's see. So, I know the first term is 18. And I just need to know 1 minus r. Ooh, well, what could the ratio be here? I'll just do 12 over 18. That's, that's 2/3 again. Okay, so it's 1 minus 2/3. But wait, I have tried to fool you again, right? That's a ratio here, but what if you did 6 over 12? That's a ratio of 1/2. This is not geometric. So there's no way you're going to use this formula to get any useful result. That formula only works for geometric sums. In fact, I wrote this to be arithmetic. Maybe you've already picked that on the pattern. I'm just taking away 6 every time. So the next term would be 0, and then it would be negative 6, negative 12, negative 18, negative 24, and I would have no sum because the terms approach negative infinity. So it's not geometric, it's arithmetic. The terms approach negative infinity. You can't use the formulas. Again, just watch out and make sure before you start using an equation, you've actually satisfied what you need to know. Okay, so if the terms, here's the thing to remember. If the terms don't go to zero, like stay close to zero, the infinite sum can't exist. Actually, should add go to and stay at zero. The infinite sum can't exist. That's true, but it actually turns out that there is a famous series called the Harmonic Series that has terms that go to zero. The infinite sum still doesn't exist. What? Well, the issue here is this isn't geometric. So the series is the sum from 1 to infinity of 1 over n. We have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Infinite series, definitely, but it doesn't have this geometric pattern. We could compute the ratios, 1/2 over 1 is 1/2, but 1/3 over 1/2 is 2/3, right? So like they're going to have a constant ratio the whole time. It's changing. And the best way to explore this harmonic series is just to go back to a spreadsheet and look at what happens. So I have that over here. My harmonic page is not geometric. Here's the partial sums. So here I do have the term, then the fraction, and then just the sum of all previous terms. Actually a lot easier to program the spreadsheet that way. Right, and so it grows, it grows, it grows. We're not adding a lot every time. We're only adding, 0.9, 0.07, 0.06. Let's just go. Let's go down to about 200. All right, it's at 5.8. Oh, but see, now it's grown past 6 at 283. This is adding a little bit each time. And it's just going to keep growing. It's going to grow past 7, past 8. It's going to grow very, very slowly, but it is going to keep growing. So the harmonic series is not geometric, and importantly, does not converge to a finite value. So the last 3 examples were actually counterexamples, things to watch out for. Just because something is decreasing doesn't mean it's going to have a finite value. It has to be geometric as well. Just because something looks like it has a pattern doesn't mean it has a geometric pattern. And just because something's geometric doesn't mean it's going to converge, because you have to have a ratio less than 1. So please watch out for those common traps. And don't get so excited because the formula looks super easy. It is, but you have to be very careful. We've already looked at those nice pictures. So let's close this out today. In summary, we have finite geometric series, which have a fairly complicated formula for how to find their sums. But you can just apply it using your calculator and you will get a result. For the finite sum of an, I wrote finite. Why did I write finite here? Get out of here. The sum of an infinite geometric series is a1 over 1 minus r, because the r to the n term cancels out. Basically, when n goes to infinity, as long as your ratio is less than 1 and you are sure you're dealing with a geometric series. Then the final takeaway I want you to have from this video, if anything, is that if you do have to look at an infinite sum, whether it's of a geometric or a harmonic or anything else, look at the partial sums and look for a pattern in those. It's a really powerful strategy. Sort of making a sequence of partial sums as you approach infinity. Really nice way to look at stuff, whether or not it's geometric. All right, everyone. Thank you all for watching. It's been a long one. Infinity can be kind of difficult to wrap your brain around. It's okay if you don't understand it all right away. Just practice the problems, get familiar with the formulas, and eventually it will start to click, I promise. Let me know what questions you have. I'll see you all next time.